Hello everyone, welcome to Practical Mechanics. I'm Mohsen. Today's video is about the shear stress due to torque applied to a circular shaft. Before we start, the shear stress that we are deriving its formula here is based on several assumptions. First, assume that the shaft is straight and prismatic. Center line or eye longitudinal axis of the shaft is perfect straight line. Cross sections does not change after torque applied. Material is homogeneous throughout the shaft. Material is isotropic, means all properties in all directions is the same. All directions property the same. Modulus of elasticity is the same. Shear modulus is the same for all directions. Material always Hooke's law. Then the formula that you learn between shear stress and shear strain by Hooke's law, I write it here on the top. Tau shear stress is equal to G shear modulus times gamma shear strain. That's why we say material obeys Hooke's law. The shaft has a circular cross sections. I'm not talking about any other shaft with rectangular cross sections and everything else, just circular cross sections. The angle of twist after application of the torque is small. Torque is applied above the longitudinal axis of the shaft. And the shaft has circular cross section again, and circular cross sections which are plane after twisting remain plane. After twisting, after application of the torque, they remain again plane. Shear stress increases linearly with the distance from the center of the shaft, from the axis of the shaft. It means that shear strain is zero at the center or is zero at longitudinal axis of the shaft and reach to maximum at the outer surface. Then let's start. As you see in this figure, an electric motor is driving this wood chipper. What happened? When you start on the electric motor, torque applied to the coupling by the shaft, motor shaft, and then by coupling transfer to this line shaft. What happened here? Wood chipper actually resists rotation of the shaft, and torque is applied in this end and transfer section by section to the reach to the wood chipper. But before its transfer, let's consider it. That's our shaft. That is connection the wood chipper. We called it point B. We called it here point A. And the torque is applied. Because this is an elastic material, homogeneous elastic material, it twisted, it deformed. A transferred to A prime. And a steel shaft is resisting rotation. And this is the shear deformation, shear strain in the shaft. We called it gamma. And if it is the center for the shaft, we call the radius C. And this cross section here rotates theta. We call it twisting angle. This end rotated twist as theta angle, and still other end is considered no change, no deformation. Theta indifferent, angle theta indifferent. The other end, which we assume fixed because it is resisted by the wood chipper. Then in this case, we can write a formula, relation between gamma for the shaft with length L and cross-section radius C and theta angle. I can write A prime is equal to C theta, and A prime from other things that assume that this is a part of a circle with center at B and radius as L is equal to L gamma. Then we conclude that L gamma is equal to C theta, or gamma over C is equal to theta over L. That's the formula that we needed later. And also, we have tau is equal to G gamma. Then you got here gamma is equal to tau over G. Okay? Then tau, you can write tau is equal to G gamma. Instead of gamma, I put tau over G over C equal theta over L, or tau is equal to CG theta over L. That's another formula that we can reach till now. Because of elastic behavior, because of this assumption that the shear strain is maximum at the outer surface as 0 at the center. And this is a relation between length, shear modulus, shear stress, and twisting angle theta. Okay, let's go and see what's going on inside the shaft. If we had this in a static, that because this shaft is in equilibrium, a torque is applied here and the torque is transferred to the wood chipper, there must be a torque in the other side as well. Then I cut it at here and I show the internal cross section that I cut here. Torque is applied. This portion must be in a static equilibrium. The torque that apply here must be in opposite direction. Okay, let's consider this torque inside the material, because the particles of material resist against this torque. They experience a shear stress. This shear stress share to any particles, share between particles here. I cannot consider the particles. I consider an infinitesimal element from the cross sections, a little tiny square. And shear stress here, I can show it in here. This area here, I can show by the infinitesimal, this area. And this shear, I can show it tau. Remember that maximum tau happens because maximum shear strain happens at outer surface. Maximum tau also happens at outer surface. Or we can solve it tau max is equal to G gamma max when the gamma shear strain is max. Okay, then this shear stress times this area, that's what we have. We have a small force dF, shear times dA. And take a torque or moment about the radius, about the center of the shaft, O. Then we call this radius R here. Radius R means distance from any point in the cross sections till the center. The maximum R is equal to C. Okay, that I wrote here. Then R cross dF produces a small torque which belongs only to this small tiny area and is equal to R tau r dA. Okay, tau dA, r tau dA. That's a torque. Then, if I take integration for both sides, I will find that integration of dt, which is equal to internal torque, and this is external torque, but they are equal together, no difference between them. I called it just T, is equal to integration of tau r dA. I wanted to get rid of tau because this is a function of radius. And I wanted to write it in terms of the maximum tau. If I assume that the maximum tau happen here, and tau is here, I can use the similarity of these two triangles, write tau max over tau is equal to C over R, or tau is equal to tau max times R over C. And in this integration, I can put torque is equal to integration of summation of all small torques on this cross section, summation or integration, doesn't matter, the same meaning. Then instead of tau here, I put tau max over C times R squared dA. And because this is a constant and C also is constant, I can take out from integration tau max divided by C, which is a constant, R to dA. This R to dA is a mathematical term, and mathematicians called it polar moment of inertia of the cross section, polar moment of the area. And it has a name. They called it J. Later I show you what's the formula for J. Then if we called it J, then we have torque is equivalent to tau max over C times J, or famous formula tau max, which is produced by torque times C divided by J. That's the maximum stress applied due to the torque on the shaft is equal to the torque times the radius of the cross section of the shaft divided by a properties of the cross sections. We call these properties, as I said, polar moment of area. How much is this property? Let's consider dA. dA can be taken in two forms. dA, I can take dA as a ring which is equal to the whole from 0 to C, the integration. From 0 to C, I can take R2 times D. This is 2 pi R dr. The thickness of this can be taken as dr. Okay, let's say draw this element. This thickness is dr. This is another method. One method is considered as a ring. Thickness is dr. This is another method. This is theta. Or you can say d theta, a small amount. And this is dA equal to this length is r. R d theta is this length times dr is this area. R d theta dr. That's another form. I can write this form here, or I can write the ring area here For the ring area, I take integration from 0 to the full radius. And this one is equal to 2 pi r3 dr from 0 to c is 2 pi r4 divided by 4 from 0 to c is 2 pi c4 over 2. If you write it in terms of diameter, then you can say that it is equivalent to pi d4 over 32. C is d over 2. D over 2 to power 4 is d4 over 16. 16 times 2 is 32. Then this is the value of J for a circular cross section. PD4 over 32 or PC4 over 2. That's the J. If you use this form of integration, R2 dA from 0 to C, because the variable here is R, but when you write it as R2 dr and R as well, R d theta, then you can write this double integration, 0 to 2 pi, theta changes from 0 to complete 360 degrees of 2 pi. Then I can write it as and 0 to c. Then I have 0 to 2 pi for d theta. Theta changes from 0 to 2 pi, complete circle. And again, R3dr from 0 to c. This amount is 2 pi. And this amount, we know that is, how much is it? Is again the same story here. R to power 4 divided by 4. From 0 to c is pi c4 over 2. Again, it doesn't matter which types of element you use in math. That's a mathematical term, and I just wanted to show that how much is this mathematical term. Just they called it is a name, polar moment of the inertia of the area, which is a circular here. Then, shear stress due to torque maximum happen in the outer surface. And when we reach from the outer surface to center, we approach a 0. For any points between 0 and C, if you want to calculate shear stress at any point inside the cross section, not only the outer surface, you, instead of this, you can write tau at any point equal to T R over J. That's tau at any point. And R is the distance of that point from the center of the cross sections or the axis, longitudinal axis of the shaft. Then, this is only gives you the maximum shear at the outer surface of the shaft. This is gives you the shear stress at any point due to torsion at any distance from the center between 0 to C. Let's find out what is the twisting angle theta. We reach to this formula that tau is equal to CG theta over L. And if we equivalent this to this one for maximum twisting angle actually, if you assume that you have tau max, then these two should be equal, and we reach to this formula. We do not need this element on these geometric connections, relations anymore. And then you know how much shear stress is produced inside the circular shaft with that assumption. Then tau max, you can say CG theta over L is equal to TC over J. You can get rid of C in both sides, and theta is equal to TL over GJ. This is the twisting angle formula. You know how much, if you exert a force, torque, on a shaft, and after the shaft transfer the torque to any machine. But before that, during this transmission, the shaft is deformed, twisted. How much? Depends on the length of the shaft, depends on the modulus of elastic shear modulus of the shaft, depends on the geometric of the cross section of the shaft J, depends on the length, depends on the torque, depends on the geometric properties of the cross sections, and depends on the shear modulus of the material of the shaft. The amount that the shaft during transmission of the torque is twisted is not transmitted without deformation. Always any elastic shaft deformed and transferred up. And you can find that. And there is a word for that, that if the shaft deformed less or the shaft deformed large, they called it, they have a term for that. They called it torsional stiffness of the shaft. What is it? The amount of torque required actually T over theta, which is equal to, if you find out T over theta, which is equal to G J over L. Depends on the material, depends on the cross sections properties, and depends on the length of the shaft. The amount of torque that is required, for example, produce 1 unit of deformation, twisting angle. Theta is called twisting angle. Then this is called torsional stiffness of the shaft. Torsional stiffness, T over theta. Yeah. You know the amount of, how to calculate the twisting angle. You know how to calculate the shear stress at any point in the cross section due to torque. And you know how to find out that this shaft actually is like so satisfy the design criteria or not. You calculate its shaft or torsional stiffness of that, and compare the different shaft with torsional stiffness, which one better satisfy your design. Later, we consider when the shaft is hollow and is not solid shaft. Why we need hollow shaft for torsion? If there is only one external load, and this external load is only torque, nothing else, no bending, no other loads applied, like transverse load, shear load. No. If the shaft is only and only under pure torque, then there is no need to put the material on the center around the longitudinal axis of the shaft. Why? Because the stress on that area or region is close to zero. Why we waste the material, make the shaft heavier in our design, and we know that this material that are here in the center doesn't help too much, because if I draw the shear distribution due to torque for a shaft, you will see that the maximum of shear stress, that's the cross sections, maximum tau max is here center is zero, distribution is like that. There is no point that I bring this material, meat of the metal here, and make the shaft heavy. For me, it's better to make a hollow shaft from internal radius to outer radius. And then send the material from the core to the outside, because outside just carry larger shear stress. And I need the material over there. I need the particles as a soldier in here around the outer surface to carry actually the maximum shear, but not here. Here is close to zero. This is only and only when we have only shaft for transmitting the torque only. If there is a bending, story will be different. For bending, we need the material in the center as well. For transverse shear load, we need the material at the center also. Then, this is the story of a shaft that a prismatic circular cross-section shaft, elastic Hooke's law obeying and isotropic material shaft is subjected to torque. Okay, thank you for watching. See you in the next video.